Thank you all for being here and welcome to You Shall Not Password. My name is Eli Holderness and I'm going to be talking to you about authenticating your users over the web. If this is something that you've ever looked into before, you'll probably be familiar with some of the following things. A username and password-based login system. You can do all kinds of single sign-on, log in with existing accounts that you already have elsewhere. You might have two-factor authentication with something like your biometrics, fingerprints, or getting one-time passwords sent to a device like a phone, and you might even use something like an authenticator app like Duo. This can all get a little bit bewildering. The reason I care is because I work at Anvil, which is a framework for building full-stack webs with nothing but Python. And if we want to provide our users, that is, people developing apps with Anvil, with a seamless user experience where they can just check a box and add any of these options to their apps, we are going to have to understand this bewildering landscape. So what I'm going to be talking to you about today is the following: what authentication actually is, and why we should care about it, common ways to authenticate your users and their pros and cons, and finally, what makes an authentication system good. And note that I did not necessarily use the word secure there. So, what is authentication? What is this thing that everybody talks about? Why should we care about it? Well, let's say that I've built something, a web app, for example, and ideally, I have at least one user. That user might have things like, this user has stuff. This user has things like sensitive data, payment information maybe, and they might also have access to restricted actions like posting under a given online identity. As the person who has built and is maintaining this web app, I want to be able to control the access to those restricted actions and store sensitive data about them. It's all well and good, but ideally, I don't just have one user, I have lots of users. And I want to make sure that only this user has access to their stuff. Or, in other words, in a format you may be more familiar with, as a web service provider, I want to verify that a given user corresponds to a given identity so that I can make sure that they have the appropriate access to data and actions based on that identity. So, that is authentication. How do we do it? Well, it turns out that identity is really hard to define. Even in person, laying down exactly what makes one person different than another is really quite tricky. And this only gets harder when you're doing it over the web. So, rather than doing it directly, which it turns out to be a deep philosophical problem, we just use abstractions. We use things like knowledge of a password, or having a fingerprint that matches up with what your scanner thinks it should be, and so on. However, there is an issue with this, which is that these are only ever approximate. They are proxies. So, let's take a look at an example that we all know and love, classic username and password, and go through a little bit of, look at it through this framework. So the setup is you have a server that serves your web service. You have a client that is the front end that the user interacts with in order to interact with your web service. And finally, you have the user. And the user would like to authenticate and get access to their stuff. And they say, right, here are my details. I'll put in my username and my password. Client passes those on to the server. The server is able to verify that this information is correct, comes back to the client and says, yeah, this person is who they say they are. Let them get at their stuff. And under this framework, we are assuming that knowledge of this password, knowledge of this username, which typically these days is often an email address as well, is knowledge of this secret information is equivalent to identity. If I know the password, then I am that person, right? However, this isn't necessarily always true. Who knows that password? Well, of the three entities we just looked at, obviously the user has to know it. That's kind of the whole point. The client, we can just pass it straight through. The client never needs to actually store the password, so that's all good. But the server is a bit of an interesting case, because the server's function in this scenario, in this web flow, is it has to be able to verify the password. It has to be able to know somehow that that user put in the secret that defines their identity. But it also has a responsibility not to let that secret get out. Because the secret is equivalent to identity under this framework, you've really got to make sure you can't leak it. So if we were very naive, we might do something like this. I've got my server, and I'm just storing records of people's usernames and their password. Obviously, then I get passed the password by the client, and I can just go, yeah, it matches, great, cool, let them in. But if your database is ever leaked, if anybody ever gets access to all of these records, suddenly all of your users have their identities completely compromised. So what we do instead is we use salted hashes, and this hash in blue is a one-way function that basically takes an input string and turns it into an incomprehensible mishmash of characters and letters and all of these different things. And at the end, we've added a little bit of random data, and the purpose of this is that this bit of random data is different for every password that you would feed into this hash function, and it makes brute forcing, if you know the hash function, the salt prevents an attacker from just brute forcing lots of passwords using the hash function. It all gets a little bit involved. But basically, what it means is that the server doesn't have to store the password. It can store this inscrutable string of characters. So instead, what you end up with is you store my username and the salted hash of my password. And the way that we do it, the way that it's commonly done, is that you have like a little $, and then after that is the big long inscrutable string of numbers, and before it is the salt. And so when the server gets the password sent to it by the client, it can go, well, I know I need to add that 7AF, that little bit of extra data to the end of this, feed it into my hash function, compare it to what's after the $, and then I know that these things match, and the server never has to store the password. This is much, much better than storing it in plain text. Don't ever store passwords in plain text. But for most passwords, if somebody gets hold of your salted hash, it's still game over, right? Because if I have that salted hash, and therefore I know what salt to pass in with the password, and there are only like a few hash functions that ever get used, I could just brute force, like with a dictionary attack, lots of common passwords, right? A password like Eli's password would get cracked very, very soon if somebody specifically wanted to target me and had my salted hash. So what you end up with is most passwords are kind of insecure unless they look something like this to start with, right? That's hard to remember. And thinking about who else has to know what's going on, what the password is, let's go back and think about our user. Unfortunately, users are people. And this means things like they can forget their password. If you are having to remember passwords that are big, long, inscrutable strings of characters, that's hard to remember. And moreover, if your user forgets their password, this thing that defines their identity as far as your system is concerned, you need some way to let them reset that password without compromising your security. Users can also be can be tricked into giving away their password. So this is a common attack known as a phishing attack, whereby one website buys up a domain that's very, very close in spelling to another, pretends to be that website, and then the user goes and puts their password for the legitimate website into the false one. And this means that, suddenly their password for that legitimate service has now been compromised. Users can be tempted to reuse passwords, particularly if they've gone to the effort of memorizing some inscrutable string of numbers and letters. You're going to want to use that everywhere. But if you've been tricked into giving away your password through a phishing attack, whoever's now got hold of it can go and try that password with every online service they think you might have. And if you're reusing that password, all of those accounts are now compromised. So this is our classic username and password model, and we can see that it's not quite good enough, right? So how can we do better? One thing we in industry have landed on is the idea of multi-factor authentication. And this is like, you sign in with a username and password to your bank, and you get a text to your phone saying, this is your one-time password, you need to enter that as well, requiring more than one thing in order to authenticate. We have my single Lord of the Rings meme for this talk. We've had one, yes, but what about a second authentication factor? If we think about identity as authentication as an abstraction over identity, it's essentially the same as saying, well, if one abstraction fails, if somebody else did get hold of my password, let's require another kind of success as an extra layer of security. And there are these factors, these authentication factors, that like the proxies that we use for identity, generally fall into three camps. And you may have heard this before if you've sort of looked into this in any detail. You've got things that you know, like a username and password. And the risk here is that you might not be the only one who knows them. Right? You can forget your password, you can be tricked into giving it away, and you can be tempted to reuse it, meaning that it's less secure. You've got things that you have, like physical access to a phone that can receive one-time passwords. Obviously, you could lose these physically, you could have these physically stolen. And then lastly, you have things you are, biometrics, so like fingerprints, or if you're getting really fancy, retinal scans. And the downside with this is that you can't actually tell nationwide that this is my fingerprint. What you're actually doing is you're using a piece of hardware, a scanner, to verify that for you. So you inherently have to trust that hardware. Also, if that's compromised, I can't just get a new thumb. It's a lot harder to reset biometrics. So, if you're doing multi-factor authentication, you have a few options. You might ask for two things that you know. But an issue with this is that if somebody's got hold of my password, if somebody's got hold of one thing I know, right, they've tricked me into giving it away, or they've cracked it because they've got access to the database, they could probably use the same method to get hold of the second thing. So it's often, what you'll see in two-factor authentication is you require two different types of factors. So something you know and something you have. And this is better because you probably can't use the same method. Just because you've managed to crack my password from having database access doesn't mean you can steal my phone. So that's two-factor authentication. Water break. Everybody drink some water. There are lots of options for what you might choose as a second authentication factor, and we are going to go through them now. First up, and my personal favorite, are hardware authentication tokens. And these look like this. They can be something like a YubiKey, a USB, or a small roaming device is what they're called. But they can also be built into larger devices like a phone or a laptop, and they work pretty much the same. And the way that they work is they use public key cryptography. So very brief primer on public key cryptography for anyone who's not already familiar. How this works is that there is a pair of keys that defines your identity. You have a private key. You don't tell anybody. Very, very secret. You have a public key that you share with everybody. And what you can do is when you send a message to somebody, you can sign it using that private key, and anybody who has the public key will be able to verify that it was signed with that private key without you having to give away that private key. And this means that anybody receiving a message can have a very high level of trust that it was really actually sent by you. And what a hardware authentication token does is it just embodies that hardware, that private key. It's baked into it at the hardware level. So the way that you use them to log into a service looks like this. I've got my user, their client, and the server, just as we did before. And the user says, I would like to log in, please. And the client goes back and says, well, we ask our users to have hardware authentication tokens. Server, please issue an authentication challenge. And this is a message that the server wants to see signed by that private key and return to it. So it does that. It sends an authentication challenge to the client. The client says, I've got an authentication challenge. Please present your hardware token. The user does, and this can be plugging it into the computer. It can connect via Bluetooth, NFC. If you're on a phone, it might be you unlock it with your fingerprint. And then that authentication challenge is passed by the client directly to the hardware token, which then does all the cryptographic processing. It signs it with the private key that's baked into it. And then that signed response is sent back to the client, which then sends it onto the server. The server is able to verify it using its knowledge of your public key, and then go back to the client and say, this person is who they are. Let them get at their stuff. And there are some really interesting things about this flow, one of which is that this device knows about the web service. That authentication challenge from the server was passed directly onto the device itself. And one of the things this does is gives you very strong protection against the phishing attacks that I mentioned earlier. Your hardware token is much, much better at spotting fake websites than you are. Another thing is that the private key never leaves this device. All the processing is done on the device itself. That authentication challenge is signed within that hardware, not your computer. And actually, if it's a key that's built into a larger device, there's actually a layer of separation there, like in hardware, that ensures that this is true even for ones that are built into laptops and phones. And this means that even if your computer is riddled with malware, that private key cannot be extracted, which is pretty cool. And even if your computer is riddled with malware, one thing it might do is it might send lots of spurious authentication challenges to a connected device and try and brute force the private key that way. And for that reason, the device will often require user presence. So if you've ever used a YubiKey, you'll know that often you have to press a button in order to make it do the cryptographic processing. And for devices, keys that are built into devices, you will often have to do some kind of gesture, like using your fingerprint, in order to make the authentication key do the thing. And this means that even if I connect my YubiKey to my laptop's full of viruses, and they start spamming my YubiKey trying to figure out its private key, I would have to press the button every single time in order to do that, and I'm not going to do that. So, hardware tokens, they're great, right? Everybody should have one. Everybody should have one, love it, cherish it, don't lose it. But there are some downsides, and one downside is that they are expensive. If you are going to build a web app, and you want everybody to have to use one of these, you're going to have to be okay with the fact that some people don't have them, don't want to buy them, don't have access to them, and that is going to limit your usership. The other issue is that you could lose them, right? I've lost key rings before. I know I could lose a hardware authentication token. And if a user does, this thing that defines their identity according to your framework, you need a way to let them reset that and register a new hardware token without compromising your security, right? You might notice a theme as we go on. So, hardware authentication tokens. One other option that you have for two-factor authentication is one-time passwords. So for this is another thing that you have. This is when you try and sign into a bank and it sends like typically there's 6-digit codes, and you have to then input that in order to log in. And these are pretty good. They're a way of using hardware that isn't necessarily a hardware authentication token, especially if you're using texts. Lots of people have phones that can receive texts, and you also have the option of using authenticator apps that are sort of built into your smartphone, or installed on your smartphone, I should say. And the way that you log in with this looks like this. You've got your user, your web app, your server, and your device. The user says, hello, I would like to log in. And the client goes to the server and says, hello, please generate a code for this user, and send it to the device that we have on file for them. That happens, and the code is sent to your device. The user then reads it and inputs it, and the client goes, yes, I can verify this, and lets them in to their stuff. And this is actually, it works. This is a very, very widely used system. One drawback is that if you're using text messages, right, phone numbers, access to a phone number that can read texts is not actually that secure. If I go to your phone service provider, I walk into Vodafone and I say, hey, this is my number, but I lost my SIM. Can you issue me a new one? And if they're secure, now you're relying on the shop's security and the system's security to not let just a random person do that, because if they do, they could read your text. They can have access to any one-time passwords sent to that device. Another issue is that you can lose your phone. And you need to allow people to reset this device in order to maintain access to your service. Another option is magic link login. Hands up here who uses Slack. Yeah, Slack does this. It's really cool. And what you do is you input your email, and you get a link, and it takes you to an authenticated session in that service. And looking familiar? It's very similar to the one-time password flow. You put in your email. The client says, hey, server, will you generate a session token for this person to log into their account? The server does that, sends it to the email. The user then clicks on that link in the email, and it takes them back to the web app, but now they are authenticated and they can get at their stuff. And one of the reasons this is pretty good is because if you're on the web using web services, you probably have an email account, even if you don't have a phone that can receive text messages. So one of the talks, I forget which one it was yesterday, the speaker mentioned a friend who has text-based two-factor authentication, but doesn't have signal in their house and have to run to the end of the road to get the code. If you're trying to access the web, you probably have access to your email, so this is one way of mitigating that problem. And it can all happen on the same device, right? I can access my emails from my phone, click on that link, and be taken into the Slack app. So it works on, you only need one device to actually do this. On the other hand, people can lose access to their emails. We actually see this a lot at Anvil with student accounts. People who signed up under a .edu account or something that they lose access to once they graduate, and they have so many different accounts registered with that they don't realize until they've actually lost access to that account. And then how do you verify their identity? You need some way to let them reset it without compromising your security. I'm going to sound like a broken record on this, and you will see why. One of the reasons that, anyway, we've now looked at a bunch of different options for two-factor authentication. And now I want you to think about how many online accounts you have, right? Like Facebook, Google, Twitter, Tumblr for me, because I am that person, Pinterest, Etsy, whatever. And think about setting up two-factor authentication for all of them, right? That's a lot. That's a lot of things to manage. Alternately, let's say you have a software company or you are like the sysadmin. Think about how many online accounts an average employee needs. GitHub, Slack, maybe Trello or Jira, and you will need to not only set up and administrate all of these, but put multi-factor authentication on all of these. It's a lot. So two-factor authentication is great. It greatly increases the security of all your online identities, but that's a lot of overhead. What if we could just have one central account that we have two-factor authentication set up in once, and we could use that security everywhere? This is the idea behind single sign-on. And the idea behind single sign-on is that you have the web apps that we've been talking about previously, now in this framework are known as service providers. They're they're the service that you want to log into, right? That has control of your stuff. But you also now have an identity provider, and the job of this entity is simply to be able to verify that you are who you say you are, and the service provider can trust the information of the identity provider. And so what SSO is essentially the service providers delegate that authentication responsibility to the identity provider. And the way that this works sort of mechanistically is as follows. You've got, the benefits of this, the identity provider, you've got one centralized identity, and the benefits of this are that you can do your two-factor authentication in one place. You can also make updates to your identity. Let's say somebody changes their name. People do this all the time. And you can change centralized identity management, right? You can see those changes and that security reflected across all of the accounts that delegate their responsibility of authentication to that identity provider. How it works mechanistically is as follows. You go to your service provider and you say, I'd like to log in. And your service provider redirects you to the identity provider. And at this point, you authenticate with whatever method you have set up. You could be using all 6 different layers of multi-factor authentication if you really wanted to. And you are authenticated there. The identity provider knows who you are and has done its job. And then it sends you back to the service provider with some kind of token of proof that the service provider can use to understand who you are and trust that the identity provider has sent it correct information. So this entire process should be cryptographically signed, right? With everybody being able to trust that the entities they're talking to has actually sent the messages that they claim to have sent. The service provider is able to interpret that token somehow, verify it, and let you log in and get out your stuff. So, how do we actually do it? Delegating our authentication to a third party. There are a couple frameworks. Sorry. I'm racing ahead of myself. I want to get to my SAML rant. Right, so benefits are web services don't need to store user credentials. This is great. It means that if my Pinterest is hacked, if Pinterest gets its database leaked, but I logged in with Google, Pinterest doesn't know anything about me other than the fact that Google is responsible for telling it who I am, right? And this means that actually, although it seems like you're concentrating all your security in one place and putting all your eggs in one basket, it means that actually smaller web apps can take advantage of the security budget of bigger places, like big identity providers, and they don't actually need to worry quite so much about their own security. I mean, they still should, but they don't need to. And users don't need to remember a lot of passwords. They only need to remember like one horrible long string of digits. Cool. One downside is that if your identity provider gets popped, so do all your other accounts. I know Okta is sponsoring here, so I will not say too much about that. But yes, you are putting all your eggs in one basket, and you very much hope that that basket does not get dropped. How can we implement it? Yes, here we go. We've got SAML, Security Assertion Markup Language, which was where this was sort of the first go at this, and it came to life mostly in corporate environments. And then we also have OpenID Connect, and this is the one that has sort of taken hold over the wider web. Let's take a deep dive. SAML. So it follows that same basic framework. You go to your SAML service provider, and for the sake of this example, let's say that this is you are an employee at Acme Corp, and this is your HR system, right? You go to your SAML service provider, your HR system, and it goes, you need to log in. I'm going to send you via a browser redirect to the identity provider, and along with that browser redirect, sort of in the query string of that HTTP, is a SAML authentication request, and this is a blob of XML data, and it should be cryptographically signed. The SAML identity provider authenticates you and then sends you back with a SAML authentication assertion, asserting who you are and that the SAML service provider should trust you. This should also be cryptographically signed. And the SAML service provider is able to parse that XML assertion and say, yes, I know who you are, you can get it, your HR system, or whatever. One cool thing about this is that it all happens via browser redirects with XML in the query string, right? And that actually means that your identity provider doesn't need to be connected to the wider web. It can actually be within like an air-gapped corporate network. But the service provider could be on the web, so I could be using my very locked down, like Acme Corp credentials to log into things that are on the public web. That's pretty cool. It's mostly kind of conceptually cool, but it is cool. However, SAML has some problems. Signing XML data, which you have to do because you should be cryptographically signing all of your communications, signing XML data is really, really, really hard. And this is because cryptographic signing works over byte strings. And here are 2 byte strings. They represent the same data, right? But they're different. They've got different spaces. And as far as XML is concerned, these 2 things are the same. As far as signing it with cryptographic with a public-private key pair is concerned, these are not the same. They will generate 2 different signatures. We need some way to understand that these both mean, oh, the issuer is whatever. And there is a way to do this. You can take both of these strings and convert them into some kind of semantic understanding, right? And this process is called canonicalization. It's hard, it's complicated. There are arguments about how to do it. There are at least three different canonicalization algorithms in the SAML specification. There is no consensus on the best way to do this. And once you've canonicalized your data, you can reconstitute it into some reliably, it's always going to be the same canonical form will always translate into the same byte string, and then you can sign over that, right? But here's the issue, is that your service provider and identity provider, you need to make sure that not only are they using the same algorithm in the same way, preferably with the same library, which is going to be hard if one is doing it in JavaScript and one is doing it in your server language of choice. You need to make sure that they're doing that the same. You need to make sure they're both getting it right. This is really, really hard. It presents a huge attack surface. There have been SAML breaches where somebody with a well-placed comment, you can just sign in as an admin with absolutely no, anybody can just sign in as an admin to SAML-based authentication systems. Really cool, really fun, quite scary. And new exploits aren't found that frequently, but they could still be found. The possibility for them, because of this complexity of canonicalization and the flexibility of XML, means that insecurity is kind of baked into SAML. So it did work for a long time. For a long time, that was how we did SSO. But now we have OpenID Connect. And this is now this is the one that you will have seen if you've ever seen a screen like this. Then you have used OIDC. You have used OIDC to log into somewhere. And the differences between, we'll see how it works, and then we'll discuss the differences between it and SAML and why this has taken over the internet and SAML didn't. But the process looks, here you go. OIDC doesn't use XML. It doesn't have this canonicalization problem. It uses JSON web tokens. These are far more restricted in format, and they do have a single best practice for canonicalization and cryptographic signing, which means that you don't have the same kind of vulnerabilities introduced by potential mismatches between those 2 things. Another difference is that tokens are parsed by the service provider. Once that token, in this case a JSON web token, is returned to the service provider, it can read it, it can understand the data out of it, but it also has the option to send it back to the identity provider for verification. And this provides an extra difficulty against somebody. If somebody sends a malicious, illegitimate token to a service provider, the service provider doesn't just have to trust it. It can actually go back to the identity provider that it knows and say, hey, I got hold of this token. Is it legit? And the identity provider can say yes or no. This also allows the identity provider to revoke access at any time, which is pretty handy if you've got lots of things that you sign into with Google and you want to stop doing that. You can just sign into Google and say, hey, revoke access for this one service. So the way that it works is pretty similar with a few extra steps at the end. In OIDC world, the identity provider is called the Authentication server. This is something it inherits from being built on top of OAuth. And a lot of the structure of OIDC is comes from having built on top of this authorization system. And the difference between authentication and authorization is a talk in its own right. I will not be going into that. You go to your service provider, Pinterest. Say, I want to log in with Google. And Pinterest says, cool, great, go to Google, go to the authorized endpoint and identify yourself. You are authenticated there using your fingerprint, your 2FA, whatever you've got going on. And then the authentication server sends you back to the service provider with an authorization code. And this is one of the OIDC flows. This is sort of the main golden path OIDC flow. An authorization code, and the service provider now has this code. Your role as the user is now done. You have authenticated. The service provider takes that authorization code and it says, hey, authentication server, I've got this auth code. Mint me some tokens. I want to know what this code means. And it hits a token endpoint. The authentication server says, yep, sure, I recognize that code. I just issued it. I can tell you what it means. And let me issue you an ID token. And this is something that the service provider can read. It's a JSON web token and say, oh, I know who this person is now, right? If it does want to do any extra verification, it can send that ID token back to an introspect endpoint and say, well, I've got this ID token. Who is this person? Tell me more about them, to give me their email and stuff. And the OIDC authentication server will not only give information if the service provider has requested it, but it can also verify that that token is legitimate. So I, as a sort of a malicious attacker, can't just send an ID token to the service provider and expect it to trust it, because it can always go back to the actual legitimate identity server and ask it if that's true. So, and at this point, the service provider goes, yeah, okay, that's been verified, have access to your stuff. And this is the one that's basically, it's taken over the internet. And because of this, you get all of the benefits of SSO. The centralized identity management, only changing things in one place, being able to do your 2FA in one place. Right. That concludes the tour of all of the options of ways that, the sort of typical ways you have of authenticating your users. Everybody drink some water. I know I need to. Right. We know what authentication is, and now we know how to do it. But what we're going to talk about in the final section is what makes an authentication system good, right? You are building a web app, and you're choosing how you're going to make sure you know who your users are. What should you consider? Well, obviously, security, right? If you've got an insecure system, you might as well not have it. And to that end, I want to go back to the first example that we looked at, which is username and password. If done correctly, this is secure. If your server only stores salted hashes, and your user remembers passwords that look like this, and if your users don't reuse their passwords, which means that they have to remember a lot of passwords that look like this, if something is hard to use securely, it's insecure. Password-based systems are hard to use securely for your users. It requires difficult behaviors that are not intuitive and it's not usable, right? And this means that you'll end up with users doing things like, reusing passwords, putting them on sticky notes on their computers, which is actually not as bad as reusing them, honestly. And the thing is, you might say, well, I have really clever users, right? I have sophisticated users. Maybe my users are also developers. They know all this stuff. Smartest person I know, put their master password into Slack. Doesn't matter how clever your users are. You need to build your system to account for the fact that they will make mistakes. So if something is hard to use securely, it's insecure. So we have now security and ease of use. And you might think that these two things are kind of in tension, and to some extent that's true. But there's also a consideration where, like, let's say that I want to use one-time password-based system for my web app, and I don't want to use text-based one-time passwords because they're insecure. Reddit had a leak because their admin team was using text-based one-time passwords, and somebody managed to break that. But the thing is, maybe my users don't all have smartphones, so I can't use an authenticator app for that because they don't all have devices with that capability. Because text-based messaging, text message-based one-time passwords are usable, they're easy to use, they're easy to access for a lot of people, unless you live in somewhere with no service and you have to run down the road to get your code. It makes it more accessible. It's better than not having anything as a second factor, right? So just because something is not the most secure thing in the world doesn't mean you shouldn't consider it as an option that's better than nothing, right? So we've got security and ease of use, right? And again, if done correctly, SAML is secure. If you make sure that your SAML libraries are up to date and cover all known vulnerabilities, if you make sure that your service provider and your identity provider are using the same ones and they've both got it right. But here's the thing is that's a lot of overhead for you. You've got to stay on top of like people who are trying to crack these kind of systems and reporting their findings. You have got to do a lot of overhead when you're actually setting up your system, do a lot of research into like why SAML is difficult to do correctly. As far as a user is concerned, it's super easy to use. It's single sign-on. But SAML-based systems, although they can be done securely, very rarely are. If something is hard to implement securely, then it's going to be insecure. So we come to the third pillar of the things that I think you should care about when you're doing an authentication system is security, ease of use, and ease of implementation. Usability doesn't just matter for our users, it matters for us too. We're people too. We deserve to not have to deal with things that are going to be really hard to do, or needlessly hard to do, I should say. So I think that these are the things that you need to care about when you're choosing your authentication system and designing it. You need to care about who your users are and what kind of things they have access to. You need to care about who your developers are, what their strengths are, and what they're going to have to maintain. And above all, you're going to have to care about security. So that about wraps it up. We have talked about what authentication is, why you should care about it. We've gone through all the different options that you have for authenticating, well, I mean, not all of them, but a pretty comprehensive whistle-stop tour of all the options that you have for authenticating your users and some of their pros and cons. And we have finally talked about what makes an authentication system good and the fact that usability really matters, not just for our users, but for us as well. Thank you very much. I've been Eli Holderness, and there is time for questions, or you're welcome to go and get some lunch. Any questions? I won't be offended if there aren't any.